So I was saying that this was done, it was published in 2023, and it was part of the ORION-B team. Sorry, I have to stop moving. So I think we already have a lot of context and motivation from today and yesterday of why to focus on HCN and to try to test whether it's a tracer of the star formation rate that at the end of the day is what we want to know. Well, if it trace the dense gas that is about to form stars, right? So if it's linearly correlated with the star formation rate traced by other traces, like the far infrared luminosity, as Kennicott found in 1998. So before HCN, we used to use CO, but the relation was not linear, and we don't like things that are not linear. So in 2004, Gao and Solomon found this linear relationship, and people like it because traditionally, well, HCN is considered a dense gas tracer, and this means gas that is of visual extinctions higher than 8 magnitudes. However, as we already heard today, around 9 years ago, we found that HCN seems to be related with extended translucent gas. So at 1,000 centimeters -3 and extinctions around 2 magnitudes, and slightly higher, but lower than 8 magnitudes. And then Goldsmith and Goicoechea found, well, with models, using models and collisional rates, that electron collisions play an important role when the density is lower than a few 10 to the 5, and the ionization fraction is higher than 10 to the -5. We'll hear more about the ionization fraction on Friday from Ivana. So some tools I'm going to use for this talk are, for example, the G0. So from Lombardi and collaborators 2017 paper, I think, we had the dust temperature and the column density, so the opacity from the dust. And I did the exercise to get the SED, to integrate it and get the far infrared intensity. And from this, we can estimate the G0 value, that is the far ultraviolet field. It's an approximation, but it's still valid. So the higher values are in the H regions and in the edge, while towards inside the cloud keeps decreasing to values around a few tenths of the G0. Other tools that I use for this work is non-LT radiative transfer code, like RADEX, but a little bit more complex. This code includes hyperfine structure line overlap effects, because HCN have hyperfine structures. So for a single rotational line, we don't have a single component, but we have a splitting version of the line, so with different hyperfine structure components. And then we also use new collisional excitation rates, both for H2 and electrons. And Ran already introduced the Orion-B region, so I'm not going to say much about it. It's just that the map area is around 5 square degrees. And the star formation rate is not very high, even though it's a high mass star forming region. So a bit more context on the components in the cloud, so we know what is what. These are the H2 regions, so NGC2024, and all these are related with high mass stars. While using the AV map, we can see the filaments that we found in Orion-B. mostly the clock, ORION-B9, the Hummingbird, and the flame filament. So for this work, we have several lines because we got complementary observations with the iron 30 meters, but the maps are mostly from the 1 to 0 lines for HCN, HCN, and HCO+. And then I also included for this work a great map for the atomic carbon observed with a telescope in Japan around the 2000. It was published by Gera and collaborators in 2002. So what we did was to actually spatially smooth the maps. They originally are at 30 seconds, but we spatially moved it to 120 seconds. That is still sub seconds scales. It's like 0.2 seconds. No, sorry. It's sub-parsec, so it's around 0.2 parsecs scales, the beam. And what we did is to this way we increase the sensitivity and the signal to noise. So we recover the very faint and not detected previously component here. So let's see them in a bigger way. This is the HCN map in ORION-B at 120 second beam. And if we compare with the AV map, this contour, the one more outside, is 4 magnitudes. So we see that the most of the area covered by the HCN emission is associated with extinctions lower than 4 magnitudes. So of course, lower than 8 magnitudes, that is the dense gas limit. This is HCO+, is as well very extended, similar to HCN. While for H and C, still at 120 seconds, the area recovered is way less. It's not as extended. It's just like in the surroundings of the filaments. This is the atomic carbon map. It shows also very extended emission, and for this cloud, it's tracing the gas where there's some ultraviolet radiation. So the only way to detect atomic carbon here is if there's some PDR-like chemistry. So some comments about the statistics of the maps. Of course, the most luminous map is the CO, but then the CO+ and the HCN maps have similar luminosities, while the H and C have luminosity around 3 times lower. And this is what happened when we spatially move the map from 30 seconds to 120 seconds. We recover an area of around a factor 4. So there's a lot of HCN emitting from like faint lines. And this was not detected at 30 seconds. If we compare how the line intensity goes with the extinction, I'm going to talk about the extinction instead of the column density. It was what's happening today. What we see is that the number of pixels, both for CO and HCN, is the maximum at extinctions of around 3 magnitudes here. These peaks. And actually, most of the points are, of course, below 8 magnitudes. And actually, if we go to the luminosities compared to the total luminosity for each line, what we see, if we focus for HCN here, is that around 70% of the luminosity of the HCN is actually associated with the components below 8 magnitudes. So this is translucent and diffuse gas. And it represents 96% of the total mapped area in ORION-B. If we then check what's the typical line intensity in the map for each AV range, extinction range, we see that what we recover from spatially smooth the map are these lines that are the main ones that are actually associated with the component below for magnitudes. That is going to be relevant later on. While the line intensity the typical line intensity seems to be similar for HCN for all the other ranges. Then to do a similar exercise that Ashley Vance and Goleto did for the LIGO project, what we see is that for ORION-B, the characteristic extinction, like for HCN, is the green one, is around 5.8 magnitudes. I think before Jens Kaufman said that they found in ORION-A, I think it was, an extinction of 6.1 magnitudes, so it's kind of similar as well. So 50% of the total intensity of HCN is associated with gas at lower extinction than 5.8. Given that HCN-120 have an hyperfine structure and we resolve it, we could take advantages of these and to actually fit it and get the excitation temperature and the column densities. If it is optically thin and in LTE, we can assume a single excitation temperature, then the line widths are the same for all the hyperfine structure lines, that there's no overlap. And we could get this nice map. These are at 30-second resolution to not mix the velocity components. And this is what we got from the hyperfine structure fitting method in class in GLDAS. This is only using signal above 5 sigma. So we get column densities between 10 to the 13 to 10 to the 14 centimeters minus 2. However, is it in LTE HCN? We compare the line intensities because if it's in LTE, the radius should follow a relation. That is 0.2 for the radius between the 0 and 2, so between these two, and 0.6 for the radius between the line intensities of these two. And even if it's not optically thin, it would have to follow this curve. And what we see is that most of the points in our map lies here. This is what we call that the emission is anomalous for the HCN-120. This is the spatial distribution. Everything that is not white is anomalous, so it's widespread. It's not only the core that used to be found, now is everywhere in the cloud. As I said, we carry out a multi-frequency survey towards multiple points in the region. There are different kind of environments. And what we found is that the anomalous ratios are not only for the 1 to 0, but for the 2 to 1 and the 3 to 2. So in red, you see the expected intensity in LTE, like the expected relationship between the hyperfine structures components in LTE, and definitely we shouldn't detect the satellite components for the 3 to 2, and for the 1 to 2, they should be like this one, for example, and these ones should be way weaker than they seem to be. And actually, we did the ratio between the components as well, and they seem to depart from the curve as well. This was completely new here. Then I said that another assumption of that fitting method was that the line width between the hyperfine structure components was the same. And when we fit the different components, we found that actually the ratio is not 1, but so the peak is 0.75 for the 0 to 2, and for the 1 to 2, like the ratio between them is 0.9. So the line width is also anomalous. So going back to the HCN at large scales in the map, As I said, there's there's a big difference between the faint emission part and the bright part that is inside the contour for the AV, for the extinction. And we use these non-LT models to try to understand the emission. Our models have different temperatures and also different ionization fraction. This is the abundance of electrons. And we are trying to understand the faint emission that is around the 70% of the total points. And what we see here is that the faint emissions, like the median value here, it would be, if there's no electrons at all, it would be a few 10 to the 4 centimeters per mercury, the density associated with that. And actually, if we increase the ionization fraction and or the temperature, the density is even lower, like around 10 to the 3, or a few 10 to the 3 centimeters per mercury. This is translucent gas, and definitely not dense gas. So just a 5% of the total HCN emission is actually associated with the bright emission, bright part. It is compact in the cores, and is the one associated with dense gas, while 70% of the total luminosity is the one associated with the faint emission, which is faint and is extended and is associated with the translucent gas. So what is the role of the electrons that Miriam have been asking today several times, and why is important? So as I said, our models have collisional rate with electrons, and what we see is that the line intensity and the excitation temperature increases as the ionization fraction increases. So the widespread HCN emission arises and is due to the weakly collisionally excited gas at densities lower than 10 to the 4 centimeters per 3, and this is due to an enhancement by collisional rates, by electron collision, sorry. So if we continue with the, it was supposed to be an, well, okay. If we continue with this plot, this is the HCN to CO ratio that we've been looking at today in different versions versus the AV that is kind of similar to the column density that we've been also seeing today. The ratio is a tracer of the dense gas fraction. Could explain this in this histogram. However, our histogram is a bimodal histogram. We have a new component where the ratio increases as the AV or the column density or the total column density decreases. So let's try to understand this. We mapped the points to see where it was coming from. And yeah, we see the bright points inside the filaments, that is these fronts, while this front is actually the rim, the edges of the cloud that is far ultraviolet irradiated. It would be this one. This is where far ultraviolet illumination and electrons will be important. And actually, if we compare the HCN to CO ratio with the carbon to CO ratio, that is inversely proportional to the dense gas in low density PDRs. So the density increases this way. What we see is that the ratio at low AV, so this is only contains points that comes from here, so between 0 and 3 magnitudes. The ratio increases as the density decreases in a PDR gas. So for star galactic, on the large scale, if we overlook this component, we are overestimating the dense gas fraction. So I rather left, but I'm going to talk about the HCN to ANC ratio, that it was one of the goals at the beginning of the project, and we didn't really focus on that anymore. So previous work suggested, like starting in the 90s, that the HCN to HCN ratio was a thermometer. And actually, Alvaro Acar and collaborators used ORION-A observations to prove that this radio is a thermometer, a gas thermometer. And what they suggested is that the HCN isomerization, so the destruction of HCN to create HCN, is important to explain the radio. However, what we found is that the radio seems to have some relation with the G node, so with the far ultraviolet illumination. And we wonder if the chemistry is important. And of course, yes, it is. So what we did mostly, Javier, at this step, was to use the PDR Miriam models with an updated nitrogen chemistry, specifically, these different cross-sections, photoassociation cross-sections for HCN and HCN. And then these three reactions. The first one was not included in the medium core back then. And for this isomerization reaction, that is the one that they said that it was important, there's the standard energy barrier at 1200 Kelvin. And then what Graninger et al. And Acar et al. Suggested that is a barrier of 200 Kelvin. And then these other reactions that destroyed HCN, we use an energy barrier of 1130 Kelvin. That is what the chemists in the group calculated, while Acar et al. Suggested an energy barrier of 20 Kelvin. So the PDR models would. So two different densities, while the same G naught, is that actually while the density decreases toward inside the cloud, the G naught doesn't change with temperature, but there's a bump due to the chemistry that I'll show you later. And same for slightly lower, like 10 times higher density. There's a bump at 2 magnitudes, but that's it. There's no relation. It's flat from outside to the inside of the cloud. And while the gas temperature decreases. So we focus how HCN and HCN are formed and destroyed in the cloud. What we see is that the photodissociation rates, like they are different. There's a different rate to destroy them, and here is going to play a role in the radio. Same for the reaction with C+, and while the cosmic rays here would imply a radio of around 1. So actually, if we look to the next one, this is the same, but so this is at fifth magnitude, 2 and 5, same density, but how the destruction of HCN changes with the G naught at the surface of the cloud. And this definitely the isomerization of HCN is not responsible, even if we choose the low energy barrier temperature. Is the most important would be the reaction with C+ or the photodissociation of HCN. While a little bit more inside the cloud is either the cosmic rays or the secondary electron, the photonic ultraviolet photons from the cosmic rays. And again, not the isomerization. And to finish, I would like to show you these plots that kind of resemble the Kennicutt-Smith law, but pixel by pixel. What we find is 3 different regions for CO, HCN, and CO+. So the white and black and white fits here, and 1, 2, and 3, and for HCO+ as well. That while for HCN, we only find a single regime. So for high infrared intensities, the relationship between the line intensity and the far infrared intensity, or the G0, that is because they are comparable, is superlinear, like between 1.65, while the relation in the low far infrared intensity is sublinear. While, as I said, HNC is always superlinear. What we take from here is that actually different gas densities, excitation regimes, and the chemistry start forming regions. So here that it would be mostly, these points are mostly related with NGC2024, that is the most bright HC region and extended. Have different conditions to the non-star forming environments, which have lower density and lower far ultraviolet illumination, that it would be the sublinear relation here. So this, I can leave here my summary and my view of ORION-B from the HCN point of view.
Thank you. Yeah. Yep. Time for questions.
I'm interested in the anomalous emission part. So is it possible, I mean, can you rule out that the anomalous ratios between the alpha points is coming from two components that have different excitation temperature and different taus, and when you fit with a single component, it doesn't fit well? Because you have a very nice and extended emission from the faint components, and then you have, that could be like in front of the really dense gas.
Like an envelope, you mean?
Yeah.
No. So in the paper, we compare the models of how would be the emission and the radius for this kind of envelope, like a scattering. And this is not the case. Like there's a figure in the paper where we compare that scenario versus a non-scattering scenario, like a core with envelope, like a core with an envelope that is scattered the HCN emission. That I guess is what you mean.
Two volumes.
Yeah. So, but no, it doesn't work. At least the models don't work, and we don't have higher angular resolution. Well, we have for smaller scales, but yeah, no. It's large scale anomalies.
Yeah, but maybe following up what you were saying, could you show again the plot with the lines, the spectra? Because it looks like if you take as reference the strongest one, the faintest one is always underestimated. But if you do the opposite, then, so you take as reference the faintest one, it's gonna be the most intense that is underestimated, like in case of a high tau for that component. So maybe that could be really possibility.
For the position one, they are mostly likely optically thick. Yes. But for the others, I don't think I have I haven't put it here, but I have an estimation of the taus because I have these autoplogs as well. Yeah, and they are not really that optically thick. They are around close to 1.
Thank you, Miriam. Very deep analysis. Let me know, allow just one comment on a bit the semantics, what we call dense gas and not. Because I think from an extragalactic point of view, if you have something like 10 to the 3 to 10 to the 4, it's reasonably dense. And I think there are some some evidence that this might be roughly the threshold where gas tends to decouple from the molecular cloud and becomes gravitationally unstable. Anyways, my question is about this, the second branch that you find in the HCN to CO correlation. So how much of the luminosity of the HCN luminosity is actually in that second branch? So how much of the emission does it account for?
Yeah, so
Okay.
is where is it? Here. So it's all the gas below 4 magnitudes. For HCN, is the red one, so around 30% of the luminosity.
Okay, thanks.
So everything here and below.
Yeah, depends a bit when you where you put the threshold, but
So our limit, while in W49, I think your limit is 2 magnitudes. Here, the limit is like 0.9.
Interested in the sense of, I mean, exogalactically, you average a lot together. Then the question is, how much of contamination do you potentially have? So if you believe that this branch is occurring in every molecular cloud with star formation, how much contamination do you actually have in your HCN intensity, right? That's the question.
I'm not sure. So I know that, so it's like 70% is not in the dense gas. So 70% of the total luminosity is not in dense gas. 30% is in that low branch. So it would have to be there. But what I don't know, and I think that's Antoine's work, is how things average when you work in a diluted beam.
If it's centered to what we're looking at, you expect this proportion of luminosity going to the second one to increase as the density goes to much higher density. To expect this pollution of the luminosity from emission to decrease. I think my perspective on this is that is a good question. By smoking dense gas is a lot of the gas is already dense. The PGF is already centered on high.
Okay. I'm going to ask myself because I've been refraining myself for asking. Sorry. Just to comment on this.
Yeah.
And it's actually related to this bimodal trend.
Yeah.
One of these, I mean, I understand that this bimodal trend, the new one, is related to this platforming in these lines, indeed, which is, I mean, it puzzles me because it looks like all lines are keeping the same intensity level. And that seems, I mean, I could understand that the HCN doesn't vanish, but the fact that they keep, I mean, all lines keep that platforming level, it surprises me.
So
I don't know if that's...
it continues at a similar level because of the electrons. The enhancement from electrons, it increased the line intensity in a factor 10.
But what about CO? Because CO is not is not sensitive.
CO, I think it moves from the optically thick to the optically thin. So I think actually it continues decreasing the intensity. That's why the ratio keeps increasing.
I mean, I find it sort of conspiracy.
I mean, this is the data.
Yeah, when I don't know, it could be related to the clipping issue we were talking about this morning. I don't know if there is any in the super low signal to noise ratio, if there is any clipping issue, because I saw the maps were not complete. So maybe that's affecting this. Yeah, I mean, you see areas around.
So these
there are holes over there.
The image is not the one I use for the
okay.
For the analysis. This is for
displaying
the image.
Okay. Okay.
Yeah.